Hey everybody, welcome back. Mr. Smith here. In our last video, we talked about how velocity time graphs are one of the all-time best tools in physics for turning complicated situations into graphs which tell a story, and then using those graphs to pull out basic math. So we're going to continue along those lines. We're going to show you some of those more complicated situations as we go. So we're going to start off with a straightforward one where a hockey player pushes on the ice, speeds up from 2 meters per second to 10 meters per second, and they ask us to figure out its acceleration. So you'll remember from last time that when we graph a situation like this, we've got a v1 of 2 meters per second. We've got a v2 up here later of 10 meters per second. That the way we figure out acceleration is by getting the slope of the line. So slope's easy enough for this one. It's just like we've been doing. It's just change in velocity. So v2 minus v1, that looks like 8 meters per second, over the run of the graph, and this whole story takes place over a time of 4 seconds. And so we'll just pop that guy in there, and we get that the acceleration of the hockey player was 2 meters per second per second. Okay, so slope equals acceleration, same as it did in the first deck. All right, this one's a little different though. If they ask us to figure out the displacement of the hockey player over the 4 seconds that he was accelerating, look what happens. Here's the graph again. We've got velocity 1, we've got velocity 2. But you should notice that if I start thinking about velocity, or displacement rather, as being the area of the shape, I'm going to draw a line down from my graph and dot that right into the t-axis. And what we said was if you color in all the area from the t-axis up to the shape or down to the shape if it's down here, that area is going to represent the displacement of the motion. Okay, so here's the thing. This shape right here wouldn't be a triangle. It's not hard to figure out what it could be if you think about it. What it could be is a combination of shapes. And what I'm always going to be able to do in Physics 1 is just break up shapes that are complicated into shapes that are actually a little bit simpler to deal with. So if I call this height from here to here, big H, we just looked at that. That was the rise that we looked at in our last example, and the height there was 8 meters per second. If I go down to this little box right now, I'll call that little h, and let's just say that that little h equals 2 meters per second, because that's what it is. What I've got now is a triangle in a box. And I know that the base is the same thing as the run of the example I just used a second ago. So the base of both of these guys is 4 seconds. So what I'm going to do is just talk first about the rectangle, and I know that the area of a rectangle is just base times height. So I've got 4 seconds, and we'll get right to work on this one, times the height of 2 meters per second. And I put those together, and I get that the displacement represented by this area right here is 8 meters. Okay. So similarly, if I go up here and call up the area of a triangle, that's 1/2 of base times height, and I'll just pop in numbers, and I get 1/2 base times height is 1/2 of 4 seconds, and then 8 meters per second is the height right there, and looks like 1/2 of 32, and that's going to be 16 meters. Okay, so just like we talked about in the last slide deck, if you want the area of a compound thing, you can just chain them together, and so the total displacement for this motion would be, 24 meters. Okay? All right, so that's one example. Next one, a little bit different. In this one, a car backs up, so it's going to the left now, maybe, speeding up from rest to a velocity of minus 8 meters per second in a time of 8 seconds. So they ask us what's the car's acceleration. Okay, so we can graph that. A car that goes from rest, that's 0 meters per second right here, to minus 8 meters per second in a time of 8 seconds, just has a diagonal line like that. The thing is, it's a good reminder that there's positive territory on the graph. These represent all the motions that go to the right, and there's negative territory. So these represent all the motions that go to the left, or up and down maybe. So same as before, if they want us to get the slope, that's pretty easy to do. We'll just zero in on the rise and the run. So v1 here is 0. v2 is equal to negative 8 meters per second. And this is one of those situations where the rise of the graph is a little weird looking. Some people get thrown off by this, but the rise of the graph is actually a fall. And that's actually language that you're going to use in class, because sometimes if you're in negative territory, or if you're in positive territory and diving, any situation where your graph is going down, the slope is going to come out minus because it's a downhill slope. So the rise of this is going to be v2 minus v1, so minus 8 minus 0. And you can see it's actually minus 8 meters per second. Okay, so the slope, now that we know that, is just going to be rise over run. So it's going to be 8 meters per second. And the run of the graph is just going to be a total of 8 seconds. And so we'll pencil that in. And it looks like the slope of this guy is minus 1 meter per second per second. Okay? Let's go and check out how that works if we now go and ask about the displacement of the car. So same graph, same numbers, and let's just go talk about something that is sometimes a little bit of a cause for confusion. So here is my triangle. Got it all set up. Let's go select my pencil again because I lost it. What I've got going on now is a triangle that's in negative territory. So watch what that means. The height of this triangle goes from here, the t-axis, down to the line. Not up to the line, down to the line. And so the height of this guy is actually negative 8 meters per second. And you'll see what that does. If I go get the area of this shape by using 1/2 of base times height, I'm going to take 1/2 of the 8-second base times the negative 8 meter per second height, and come up with 1/2 of negative 64 equals negative 32 meters. So here's the thing that will happen. Anytime you have motion that's telling a story about something going on in this region of the graph, what we call negative landia, that displacement is going to be minus. So the person's just moving to the left. Again, that's all that negative velocity is. It's just moving in the minus direction. Okay? So it's one of the things that can happen. Third example is in a skate park. It's you rolling up a quarter pipe, slowing down, stopping, and then rolling backwards, all very smoothly. So you can pause this and read it further if you want to. But when we graph it, what we're going to get is a graph that looks like this. You start out with a velocity of v1 equals 4 meters per second. Sometime later, let's call it at 4 seconds, v2 equals 0 meters per second. So hopefully you look at that and you go, oh yeah, that's where I stopped. And if you're really on it, you'll say, well, this is a quarter pipe and I'm imagining you rolling up and stopping. This is weird. This is the top of your motion, the place where the velocity actually goes to 0. It does all fit together, and we'll talk about that plenty in class, so don't sweat it if you don't get it. But I'll just put down a little v3 right here, equals negative 4 meters per second. So since this question said to figure out the acceleration, the thing about getting the slope of a line is I can pick any 2 points on the line and use those to get the slope. So I could pick the first one and the last one, or here's the thing, wouldn't this be a lot easier if I picked this one, my v1 and my v2? That's what I'm going to do. So what I'm going to do is just say slope, again, equals rise over run, and that's going to be change in v over change in t for a velocity graph. And let's see, it's going to be v2 minus v1, which is 4 meters per second, and all over a time of 4 seconds. And look at it again. The downhill slope has a negative value when we go and figure it out, minus 1 meter per second per second. So let's go check out what the story looks like when they ask us about the displacement. So if you look at the graph, it's the same graph as before. You might want to think about shading in areas, and I certainly am. I'm going to look at shading in this area right here. So from the t-axis up to the line, so from here up to here. And then we're going to practice doing something that may be a little weird for you. So we're going to drop a line from the t-axis down to the graph and shade this in. So this one trips a lot of people up, but what I want to do is always think about the area of shapes as being the shape between the t-axis and whatever shape our graph is making. So if you do this, then you might notice that these two shapes look really similar to each other, and I think they're actually symmetric. So what I want to do is just think about what answer I might get. I think this is going to end up being positive area. This is going to end up being negative area, and they're going to cancel. I'll show you how. So this first value we just looked at, we said that that was 4 meters per second. And so that means that the height of my first triangle over here is 4 meters per second tall. Okay, so what I'm going to do is just pull together a little 1/2 base times height for this guy. So 1/2, the base of this first triangle is 4 seconds, and the height is 4 meters per second. Put those together, and we get a total of 8 meters. Okay, so what's the difference with this triangle over here? Let's go and see if we can get a little bit of a more fun color different there. And let's go paint this guy with red. So similar shape, similar numbers, 1/2 of base. He's also 4 seconds long in the base. And then the height, what we did last time, hopefully you remember now. The height of this particular triangle is -4 meters per second. And so if I apply that correctly, then I go and figure out that the area of the sky is -8 meters. And so, like we figured out, what goes on here is you roll up the ramp, you stop, you roll back the ramp, and everything's symmetric so that by the time 8 seconds rolls around, you're back where you started and go on the same exact speed, 4 meters per second, but just in the opposite direction. Okay, so that's a lot that's going on with velocity time graphs. Bring your questions to class, take care of yourselves, and see you next time. Bye-bye.